Okay, it is about 2:03, so we're going to get started. Good afternoon, everyone. My name is Erin Farley, and I'm one of JRSA's research associates. For those of you who may be less familiar with JRSA, it stands for the Justice Research and Statistics Association. We are a national nonprofit organization dedicated to the use of research and analysis to inform criminal and juvenile justice decision-making, and we are comprised of a network of researchers and practitioners, which at the core include directors and staff from the state statistical analysis centers. So before I welcome our presenter, I want to let attendees know that we will have a skill building webinar in May. It is scheduled right now for May 18th. It is not posted, but it will be available for registration very soon. And it will be on ArcGIS and will be presented by Elizabeth Roth from Temple University. So we're really excited about that, and that's going to be in May. So today it is my pleasure to welcome you to our webinar addressing area under the curve analysis by Doug Spence. He is the director of the Office of Research and Strategic Planning and is at the West Virginia SAC. So welcome, Doug. And before we go further, I want to thank our partners at the Bureau of Justice Statistics for helping to make this webinar possible. And I would also like to cover a few logistical items. We will be recording today's session for future playback, and the link to the recording will be posted on JRSA's website, and we usually post that, the following day, so it should be up tomorrow. And today's webinar is being audiocast via both speakers on your computer and teleconference. So we recommend listening to the webinar using your computer speakers or headphones. To access the audio conference, select audio from the top menu bar and then select audio conference. Once the audio conference window appears, you can view the teleconference call-in information or join the audio conference via your computer. If you have any questions for the presenter or you would like to communicate, hold on one second, let me catch up with myself on PowerPoint. Okay, so there's the information of the call-in information, and then one more, here we go. So if you would like to communicate, if you would like to ask a question, feel free to post those throughout the presentation, and we will be, on my part, I will be sharing those with Doug as we go through to see if he can answer them at that time, and we can also hold questions to the end if anybody would like either or. So feel free just to, chat, add a question by going through the chat feature. And here we would prefer that you either do all participants, which is right there in blue, or host, presenter, and panelists. So this session is scheduled for approximately 1 hour. Usually sometimes we do go over to between 1 and hour and a half, depending on the questions. So we hope that you guys are able to participate and hold on to the end, because we do have polling that we save into the last 5 minutes. And so we would love to get your feedback on what you liked about the session. So when we do that, please take a moment at the end to fill out that poll. If you do have any technical difficulties throughout this webinar or you get disconnected, you can reconnect going through the same link that you received to join, or you can also reach out to Jason Trask at jtrask@jrsa.org. Okay, and so I think that is it. So what I'm going to do, one more thing. So what we are doing, this is kind of a recent thing we've been adding into our webinars, is that we know that we have people who are viewing as a group. And so we are really trying to get a close to accurate number on how many people are actually viewing during the live webinar. And so if you do have a group with you, we would ask that you please go to the chat window and type in the name of the person registered and the total number of additional people that you have in the room. So this, again, just really helps us keep track of how many people are actually attending the webinar, and we really appreciate it, so thank you. All right, and so with that, I'm going to pass it off to Doug, and with that, I'm going to drag the little magic ball and give it to Doug. And so it is, oops, wait. Is it working? Hold on one second. Yes, here we go. Okay. All right, Doug, it's all yours. Thank you.
Okay, thank you, Erin, for the introduction and for the magic ball. As she said, I'm Doug Spence, talking today about area under the curve analysis, which is an increasingly commonly used technique in criminology and really in a variety of fields that are interested in evaluating the performance of predictions. And what I hope you guys will all see today is that this is a technique that's not only, pretty easy and straightforward to use, it's something that has a lot of utility in a lot of different applications in criminal justice, everything from evaluating risk and needs assessments and doing recidivism analysis, outcome studies, and all sorts of stuff. So before we get started today, I do want to give you guys a little bit of an overview of what I'll be talking about. So I'm going to start by talking a little bit about the background and historical context of AUC analysis, because it's something that comes from signal detection theory. We'll talk a little bit about sort of the broader issue of evaluating binary predictors or classifiers. Also talk about the receiver operating characteristic curve, and that is the curve that area under the curve analysis is looking at. Then we'll get into the AUC statistic itself and how to interpret it. Then I'll walk everyone through how to conduct AUC analysis and SPSS, and we'll wrap up by talking about ways you can use AUC analysis and some kind of interesting and useful ways to supplement and enhance analysis results that you might be doing. All right, so to start off here with some background and historical context, AUC analysis was first developed in World War II by basically radar operators. So that ROC curve originally stands for radar receiver operating characteristic curve. And basically what they were interested in doing was figuring out a way to maximize the performance of radar. So they wanted to basically maximize the amount of correct predictions that they would have. So in other words, the true positives, so that they would spot every enemy aircraft that would come in. So they would spot every attack. But at the same time, they also wanted to minimize the number of false positives. Because from their perspective, you can imagine you don't want to miss any attacks, but at the same time, you don't want to be scrambling the jets every time there's a flock of birds or an especially ominous cloud that comes in. So they want to minimize those false positives and maximize those true positives. And by focusing on both of those things together, they developed a technique with the ROC curve that proved to be very useful for a lot of other fields. For medicine, where they're interested in basically maximizing the number of correct diagnoses that they have, but not freaking too many people out with a bunch of incorrect diagnoses, psychology, and then, as you guys know today, criminology and criminal justice. So this is really sort of the context that it's coming from, and it's this dual emphasis on, measuring the amount of true positives while also taking into account the number of false positives that really makes the ROC a useful tool. Now, before we get into the ROC curve and the AUC statistic, I do want to talk a little bit about classifiers, because this is sort of where a lot of this language is coming from, is from signal detection theory. So it can be something that's a little bit foreign to some of us. And basically, when we're talking about classifiers or binary classifiers specifically, what we're talking about is really any type of rule or procedure for classifying cases in terms of their predictive outcome, or for classifying cases into two groups. One group where there's a positive outcome or a 1, and one group where there's a negative outcome or a 0. So we're talking about sort of classifying cases in terms of a dichotomous outcome. And in statistics, it's most often the case that classifiers are going to be your predicted probabilities produced by some type of statistical model, usually a logistic regression analysis. So that's the context that we're using here. We're basically using ROCs and the AUC statistics that are calculated from that to measure the performance of a classifier, which in this case is going to be your predicted probabilities that you produce from a logistic regression model. Now, one aspect of this, because we're dealing with predictive probabilities, we're dealing with a probabilistic classifier. So this is something that is going to have varying degrees of performance depending on where you set what's known as the discrimination threshold. The discrimination threshold is just the level at which you say that a probability has reached a point where you're going to consider it to be a prediction of a positive outcome or a 1. So, most intuitively, people would say, if it's a probability of 0.51 or more, that's a 1, and, if it's a probability of, 4.9 or below, that's a 0 or something like that. But wherever you set that is going to potentially change how accurate your predictions are. So that's a sort of a complicating factor that goes into evaluating how effective our predictors are. Now, what you can see here in terms of the little screen capture I have from SPSS, you can see what this might look like in terms of your data. So in that first column, you've got the predicted probabilities that you might save from a logistic regression model. So that pre-1, and so those are all just probabilities ranging from 0 to 1, what the model thinks the likelihood that that case is going to be a 1 is. You could have a predicted outcome that you establish based on some sort of discrimination threshold. So that column there is just a 1 if it's above 0.5 and a 0 if it's below that. And then you have the actual outcome, which is ultimately what you're going to be assessing your classifier against. How well does it predict whether cases were actually a 1 or a 0. So this is what we're talking about primarily, your predicted outcomes or your predicted probabilities that you're going to get from logistic regression analysis. Okay, so when it comes to evaluating your classifiers, there are a couple things to consider. One is that for any given case, you're going to have potentially 4 different sort of results for your classifier. You can get a true positive, which means that your classifier predicted that it was going to be positive and it actually was positive. You could have a false positive, which means that your classifier predicted that it would be positive and it wasn't. You could have a true negative, which is that your classifier predicted that it would be negative and it was actually negative. Or you could have a false negative, where your classifier predicted that it would be negative and it was actually positive. So there are these 4 different outcomes that you can see over there in that figure to the right. And coincidentally, that figure to the right is called a confusion matrix, which I think is kind of one of the cooler names for figures that are out there. So this is basically what's breaking down predicted class versus actual class and the different outcomes that you can get. Now, if you're going to try and evaluate a classifier's performance, there are a lot of different ways you could potentially do that. One way would be to calculate the true positive rate, which is sometimes described as the sensitivity. And you'll see that in some of your SPSS output. It'll call that sensitivity instead of saying true positive rate, but that's all that is. And that's basically the proportion of positives that were predicted correctly to be positives. You could have a false positive rate, and that's the proportion of negatives that were incorrectly predicted to be positive. You could have a true negative rate, which is also sometimes described as the specificity, and that's basically the number of negatives that were correctly predicted. And then you can have the accuracy, which is just the number of true positives and true negatives as a share of all the positives and negatives that are predicted accurately. And each of these is individually a good way of assessing the quality of a classifier, but there are some limitations to just using these, because basically each one of them doesn't consider both sort of true positives and false positives together in conjunction. So you'd have to calculate both, and you sort of have 2 numbers there. And that's also the case you'd want to calculate these for each different discrimination threshold that you might potentially set for your classifier. So that means you have to calculate this for every single predicted probability in your data set. And so really what we want is a way of simplifying all this and condensing it down so that we can have sort of one number or one figure that basically takes into account both true positives and false positives and summarizes all that information across all the different possible discrimination thresholds. And fortunately, thanks to the efforts of those radar technicians in World War II, we have that with the ROC curve. So the ROC curve, really all it does is just plot the true positive rate for a given classifier against its false positive rate, varying the discrimination threshold. So this takes one classifier, so one set of predicted probabilities from your data set, so the results from one particular model. It plots its true positive rate and false positive rate as a curve, and then each point is a different discrimination threshold or a different probability that exists in your data. And the way you would interpret this is that basically the performance of the classifier is going to get better as you move closer to that top left-hand corner of the figure. So if you were in that very top left-hand corner, you'd have a true positive rate of 1, which means that you correctly identified every single positive that was in the data. And then you would also have a false positive rate of 0, which would mean that you did not incorrectly identify any of the negatives as positive. So you would be perfectly accurate in that case. But what we got in most cases when we're actually looking at real classifiers is that they're somewhere down there kind of in the middle, sort of fluctuating along at different discrimination thresholds. And you could use an ROC curve like this to identify the particular sort of threshold that would be the most effective for maximizing the number of true positives and minimizing the number of false positives. Or you can also use it to just sort of get a visual sense of how well a particular classifier is performing. And as we'll talk about in SPSS, you can actually plot multiple classifiers in the same ROC curve, so you could compare the curves to one another, see if one is sort of bending out more to that top left-hand corner than another, and vice versa. Now, to just give you guys a little bit of a sort of discussion of how you might interpret one of these, if you're going to look at this, basically, if you looked at this curve and started at the top right where you've got a discrimination threshold of 0.30, That's basically saying what would your true positive rate and false positive rate be if you said that every case in your data that had a probability of above 0.30 would be considered positive. And what this is telling you is that it would basically allow you to get 100% of all of the true positives out there, so you wouldn't miss any positives. But if you look down at that x-axis, the false positive rate would be 0.9, so you'd get 90% of the negatives in there as well. So if you kind of think of this in a criminal justice context, this would be like if you considered above a score of above a 3.3 probability of recidivism as being high risk, and you classified everybody above that as a high-risk offender, then you would get 100% of the recidivists in terms of this data, but you would also get 90% of the non-recidivists classified as high risk as well. So you'd be basically classifying everybody as positive in this case. But what this curve does show you is that if you just increase that threshold in this sort of hypothetical case to 0.38, your true positive rate only goes down to 0.8. So you're still getting 80% of the true positives, but your false positive rate drops pretty dramatically to 0.5. So you miss a lot of those potential false positives. And so this suggests that even just kind of a modest increase in the threshold here would give you a much better prediction. And you can see that visually as it's sort of moving over towards that top left-hand corner. And that in general is what you're going to get when you get an ROC curve from SPSS or from some other tool. It's going to visualize this type of performance for you. Okay, so if that's the ROC curve, in terms of the AUC, what we're getting is a single number that summarizes the performance of the entire curve. And what the AUC is just the area of this plot that falls under the curve. So as it approaches 1, you're basically approaching having all of the area, or 100% of the area underneath the curve. And what that would look like visually would be a curve that's all the way in that top left-hand corner. As it goes more towards 0.5, that would be a curve that only has half of the area of the figure underneath the curve. So that is really all the AUC statistic is. It's just a measure of the proportion of the plot area that's under the curve of the ROC curve. And this essentially summarizes the ROC curve across all of those different discrimination thresholds. So the AUC doesn't really care what's the optimal threshold. It's not going to be something that you can use in itself to identify that. You'd have to actually look at the curve to do that. What it's doing is just summarizing that classifier, summarizing that predictor over all of the potential discrimination thresholds. Now, in terms of how this can be interpreted, this is a number that's going to range from 0 to 1, meaning that 0 would be none of the areas under the curve, and 1 is all of it is under the curve. Mathematically, it's equal to the probability that a given classifier will rank a randomly chosen positive case that's a true positive higher than a randomly chosen negative one, which is kind of a technical way of saying that it's giving you a sort of a sense of the probability that would classify a randomly selected case correctly. So, for example, if you have an AUC of 0.6, it's basically saying there's a 60% chance that any random case that you select is going to be classified in the right way. Or, you're, in other words, kind of roughly getting about 60% of the cases correctly predicted or correctly classified. Now, as far as sort of what are common standards for good or bad AUCs, the most common one you see out there for sort of an effective predictor is an AUC of 0.7. So this is something I've seen in a number of places. It's kind of the most commonly used benchmark. So that's something to shoot for potentially. But one thing that's very important to point out is that even a predictor that was essentially chance, a coin flip or something no better than chance, would have an AUC of 0.5. So that's really kind of the floor of what you should expect to see. That would be a very bad AUC if you had an AUC of 0.5. It's possible to go below that. It's possible to predict worse than chance. But just a sort of a floor for what you should expect when producing AUCs, 0.5 is basically saying you're not having any predictive accuracy. 0.7 is commonly used as, if you're getting around that, it's a pretty good predictor. But the obvious caveat to that is that these standards vary by field and application. In medicine, for example, they might want something like 0.9 because they're worried about, medicinal treatments. But the most common one I've seen is about 0.7. Now, one other thing to note, just if you look at this figure here on the right, this is demonstrating, some basically 2 different ROC curves. And what you can see from this figure is that what I was saying earlier, that the AUC statistic doesn't take into account any particular individual discrimination threshold. So what you've got there is in that one curve B that sort of bends out farther than the curve behind it A, that's one that's going to obviously have a larger AUC statistic, at least a little bit larger AUC statistic than curve A. So B is going to have a higher AUC than ROC curve A. But ROC curve A at that one particular discrimination threshold, which you can see there at that one point where curve A meets curve B, has the same predictive accuracy or the same, ratio of true positives to false positives as B. But B as a whole is better at predicting at all of the different discrimination thresholds than A is. And somewhat of a technical point, but it is an important thing to point out that, just because you have an ROC curve that has a higher AUC, it doesn't necessarily mean that it's always the better predictor. It's just the better predictor across all of those different discrimination thresholds taken collectively. Okay, so that's the basics of what the ROC curve is. It's really just looking at true positives and false positives and discrimination thresholds, and the AUC is just the area under the curve. So with that being said, here are basically the steps for how you would conduct AUC analysis after a logistic regression in SPSS, which I think would be the most common way that you would want to do this. So these are all here for reference. And basically what this boils down to is that you're going to conduct a logistic regression. You're going to save the predicted probabilities from that logistic regression. Then you're going to open up the Analyze ROC Curve menu in SPSS and plug in the predicted probabilities and your dependent variable. And so in terms of what this would look like in SPSS, if you look here, if you go and at the top pull-down menu, click Analyze and Logistic Regression, it'll bring up this logistic regression menu that you see on your left. I plugged in terms of the dependent variable there, one of the recidivism measures that I had from a study on recidivism. I plugged in just for an example, one covariate, an LCMI score, which is a risk assessment score. So that's setting up a logistic regression. And then this is the important step, is that you'll want to click the Save button there on the right. And that's going to bring up a secondary menu that's going to allow you to save particular aspects or features from your logistic regression. And what you're going to want to check there is the predicted probabilities. And so for those of you who've done this before, what it'll do is just basically produce a new variable in your data set that's going to be comprised of the predicted probabilities for each case that the dependent variable, in this case, whether you're booked into a regional jail, is 1 for that case. And that's going to be the predicted probabilities produced by that model. If you run a new model and click Save again, it's going to give you a second set of predicted probabilities that's specific to that model and so on and so forth. It's going to create basically a new variable in your data set that is the predicted probabilities. And that is going to be the classifier that you're going to evaluate with your ROC analysis. So once you've done that, then you're going to want to go back to that pull-down menu, click Analyze, and hopefully if you've got a good new version of SPSS, it'll have the ROC curve option there for you. You can go down there, click that, and then you'll have the ability to plug in from any of the variables in your data set what you want your test variable to be. And the test variable is going to be your classifier. So there I put in the predicted probability that was generated from that regression. And this is a thing it's important to keep straight if you're doing this with multiple models, which predicted probability you're looking at. So you may want to label them and do all that. And then in the state variable box, you're going to put your dependent variable and the value of the state variable that you're trying to predict, which in this case is dichotomous 0 and 1. You're going to want to type in a 1. If for some reason you had a dichotomous variable that was 1 and 2, and you're trying to predict 2 as the outcome, you're going to want to type in 2 and so forth. So you need to know what your variable is that you're using there, but you're going to type in the value that you're trying to predict. Below that, you've got some options for what you can ask SPSS to display for you. It won't automatically display the ROC curve. It'll just give you that AUC number. The AUC number is fine, but if you want to see the ROC curve, which I usually do, you can just check that box. And then you can also ask it to give you a diagonal reference line, which is just going to give you the line that sort of that bare minimum of what an AUC of 0.5 would look like. So it's just going to be a line that runs from the bottom left of your ROC curve plot to the top right, so a diagonal line across there. And that is sometimes useful to let you sort of see where your curve is in relation to that sort of bare minimum threshold there. There are also options to get confidence intervals for the AUC statistic, or to actually get it to tell you the coordinate points of the ROC curve, but those aren't as commonly used. Now, in terms of the output that you'll get something that looks like this. On the left, you've got your ROC curve plot, and this is from that model that I ran there. As you can see, it's kind of a sad ROC curve. It's not the most powerful predictor, but it is, substantially different from that line there. That's that bare threshold. So it's predicting better than chance. You can see from the area under the curve box there on the right, which is your output for your area under the curve statistics. The main thing you're going to be looking at is this area box here on the far left, and that's going to give you your AUC statistics. So that's where that is. And as you can see there, that's an AUC of 0.621. So it's not the best AUC. It's a little short of that 0.7 threshold, but it's above 0.5. So it's predicting outcomes about 62% of cases correctly. And I've also asked for some additional stuff here, the confidence interval and all of that, but it's usually not something that is as commonly used or presented, although it is sometimes. So that is the output from SPSS, and that's basically what you can expect to get. In terms of sort of why you would want to do this, there are a few things to keep in mind. One is that the AUC provides a really good summary of the predictive accuracy for limited dependent variable models, or models that are looking at dichotomous dependent variables. So that's one limitation or issue that anybody who's done a logistic regression knows, is that it's not quite like a linear regression because you can interpret the coefficients directly. You don't have a real R-squared. There are some pseudo R-squareds that SPSS will generate for you, but they do have some issues potentially. So you don't have some of those things that are as nice and useful to have as you would get in a sort of standard OLS linear regression context. And so what this does is it provides you a good, easy sort of post-estimation thing you can do to get something kind of like an R-squared for your logistic regression model. And an important thing to point out about this is it's not affected by base rates. And that means the sort of underlying rate of ones compared to zeros in your data set, or positives compared to negatives. And this is an issue because a lot of other sort of similar measures, pseudo R-squareds and other things like that are trying to get at predictive accuracy for dichotomous dependent variables are affected by base rates, which means they aren't as reliable when you have a low base rate. And in the criminal justice context, our base rates are often pretty low. If we're looking at recidivism, it may be the case that a minority of people recidivate, most people don't. If we're looking at, who's high risk or who successfully completes something, we often have situations where the base rate can be pretty low or inconsistent. And the good thing about the AUC is it's not affected by that at all. Anytime you see an AUC statistic, it's giving you an accurate measure of how many cases are predicted correctly by the classifier that you're looking at. Some other big advantages of the AUC is it can be interpreted directly. So, when you see an AUC of 0.7, that's, a random case has a 70% chance of being correctly predicted. Or in other words, roughly about 70% of cases are correctly predicted. And it's that regardless of the context, regardless of how the dependent variable is measured, of what the base rate is, anything like that. It always means what it means. And that's a nice advantage over something like a log likelihood, which can be used to measure sort of the goodness of fit for a logistic regression model, but is going to be a number you can't interpret directly. And it's going to be kind of meaningless unless you do something like a likelihood ratio test to compare two different models to one another. Another advantage of the AUC is that you can compare across models, and it doesn't matter if you're looking at models with different dependent variables or dependent variables that are measured in different units of analysis. The AUC is always going to mean the same thing anytime you do it, so that's a nice feature to have. Now, in terms of what this opens up in terms of analytical possibilities are a number of different things. One is I find it useful for assessing model specification for logistic regression models. Because it's going to play that role kind of like an R-square would. So if you're estimating a model and you're wondering if you should include an additional variable or not, you're not quite sure about that variable, you can run a model without it, calculate the AUC, put that model in, calculate the AUC again, and if the AUC stays about the same, that model really didn't enhance your predictive accuracy very much. Conversely, if the AUC jumps, dramatically, okay, that's an important variable that you're going to want to include. So it's nice for that purpose. You could sort of tweak your models a little bit, run them in different ways, and see the AUC and see how it's changing that. Another good use for the AUC is to compare the performance of different predictors for a given outcome. So, for example, if you have a couple of different risk assessment tools and you're wanting to see how well they predict recidivism, you could run models with each of those and then see how they predict and compare those AUCs directly. And the one that has the highest AUC is the best predictor. So that's a useful tool to have. Then you can also look at it the other way and use one predictor with different outcomes or populations. So you could see, does that risk assessment tool predict different measures of recidivism in the same way? Or does it predict, things like misconduct in prison or other sorts of outcomes you might be interested in predicting? And you can also run the model with subpopulations from your sample and see, okay, is it just as predictive for males as for females? Or is it just as predictive for, different types of offenders with different, types of needs or offense types or something like that. So it's going to open up a lot of different possibilities for comparing models to one another with logistic regression. And that's nice because without the AUC, really all you're stuck with is just sort of comparing odds ratios for variables, and those things are more prone to fluctuate, and it's a little bit more difficult to say if you're just saying, oh, this variable increases the risk of recidivism by 5% in this model and by 8% in another model. It's not as intuitive as saying this, this variable accounts for 60% of cases in one model and 70% in another case, something like that. So I've got here to sort of wrap up and kind of show you guys here some examples of where I've used this in the past. This first table here is from a report that we did looking at regression or recidivism by day report center clients in West Virginia, and the model is, or the table is sort of broken up there because this was originally a much bigger table with more variables in between. But what we can see here is we've got the usual logistic regression stuff. We've got coefficients and odds ratios and standard errors and all that. And then at the bottom, we've got the N for the sample size, we've got a pseudo R squared, and then the AUC statistic. And so what you can see here is that you've got a comparable sort of measure of predictive validity for the model as a whole across 3 different dependent variables. So you've got arrests with an AUC of 0.68, jail bookings with an AUC of 0.68, and incarcerations with an AUC of 0.82. And so what that allowed us to say was that, what we've got here when we consider this model as a whole, we're predicting pretty close to that 0.7 threshold. We've got a pretty good effective model of predicting recidivism when all these variables are included together. And this model, our model predicts, because it's the same model in each of these, our model predicts arrests at about the same rate that it predicts bookings. So they're both kind of performing fairly equally well, but it predicts incarceration significantly better. And that's something that was kind of intuitive to us because, one problem we have in West Virginia is we don't have very good convictions data. So our arrests and bookings measure, not all of those people actually committed crimes or were convicted. But incarcerations is much closer to what would be, kind of the ideal with convictions. We know that, pretty much everybody who gets incarcerated was convicted of a new offense. So we would expect that AUC to be higher in that case. So that's what we see here. So you can get a sense of sort of how you can use this as sort of kind of something like the equivalent to an R squared in a linear regression context, but for logistic regression. Now, this next table is where we did something a little bit different, a little bit more, creative with the AUC. And what we did here was basically we ran a bunch of different models. So these are all AUCs from separate models. So that's, a total of 27 in all. So 27 different models. So it was a bit of a tedious day in the office that day running all these models. But we've got 27 different AUCs here. And in the first row, you've got the AUCs from a model that includes only the total risk and need score from the risk assessment tool that we were interested in, which is the level of service case management inventory, or LCMI. And so what we can see here is that with just the total risk and need score from the LCMI, we have AUCs of about 0.62 for arrests and bookings, which is pretty close to what we had with the full model, which is about 0.68. So what that allowed us to say was that, look, if all you had for an offender was just this one number from the LCMI, we can predict almost as well as a full model that has a whole gamut of other variables related to demographics, offense type, experiences in the day report center program, length of stay, successful program completion, all this other sort of stuff. All of that collectively only gives you an additional 6 or 7% of cases that you can predict. So, all that additional information only helps you get another 7% of cases. You get most of those with just the LCMI number. So that was a powerful thing to be able to say that, even though this AUC isn't all that great, taken in itself, it does suggest that the LCMI is a pretty good predictor and that all this other information doesn't add much to it. Now, what we did below that was we took the 8 subsections of this tool and we did analyses of each of them individually. So each of these AUCs in this case represents the sort of predictive power of each of these subsections individually. And this allowed us to compare and see which subsections appeared to be the best predictors of recidivism, which were the most effective. Allowed us to identify potential areas of weakness and compare across all these different recidivism measures. And so a few things that jumped out in this was that we could see that criminal history was the most effective here with AUCs around 0.6 and then up to 0.67 for incarceration. But it also let us see that quite a few of these are pretty low. And the most surprising and the lowest was for pro-criminal attitudes, which basically is performing at about the same effectiveness as chance. So it's at about 0.5. So it's pretty much about as bad as you could get for an AUC for this particular subsection. And that was a big deal because for those of you that are familiar with the LSTMI, the pro-criminal attitude is tapping in to a lot of those kind of cognitive behavioral things that we really think drive, offending behavior and that are really the target of a lot of our interventions. So the fact that this wasn't seeming to be a good predictor was a big potential issue. And it's also a part of the risk assessment tool that is one of the more difficult to assess because it's sort of the less objective and requires, the assessor to really try to get at what they think the attitudes and beliefs of the offender are. So this was something that, in conjunction with some other results that we had from a similar study of DOC inmates, led us to recommend an additional sort of inventory that would be used to try and help assess criminal attitudes and thinking in order to help supplement and improve these results. And we're working on some trainings that will help improve performance in this area as well. So it's really sort of helped us hone in on particular parts of this risk assessment tool using AUC analysis and see where these were stacking up. Now, final thing I want to talk about is this is another example from an article that did something very similar. And basically, this is what inspired us to do that previous analysis. So we weren't entirely that creative on our own. We sort of saw a good example of this being done in another previously published study. And what they're doing here is they're looking at 3 different risk assessments and 3 different measures of recidivism and calculating AUCs. But what they're also doing that I think is kind of neat is that they're breaking up the sample. They've got the total sample there on the left, and then they're also breaking up the sample by gender. And so it allows them to compare the predictive accuracy of each of these assessment tools against each other, but also for different subpopulations in their sample. So it's a nice use of this technique. And you can see here, it does make this pretty intuitive thing where you can see, okay, if I look at women for felonies, all of these assessment tools are predicting less than they do for men. Or if I look at, this recidivism risk 3, I can see that it predicts any offense roughly the same for women as for men, and for the total sample as a whole, so forth. So it allows you to make those kind of comparisons in a relatively nuanced way without having to throw in a whole bunch of different analysis and test statistics and all that sort of thing. So that should hopefully give you all a pretty good understanding of sort of what's going on with the ROC curve and with the AUC statistic that comes from that. Hopefully what you can see from this is that ROC curves and AUC statistics do provide a pretty good, effective means for measuring the accuracy of predictions, and that there are a lot of potential applications for this. I know we focused here primarily on risk assessments and recidivism, but you could do this with any dichotomous outcome that you're interested in. And with any non-dichotomous outcomes, if you can find a way to sort of dichotomize it in a useful and sound way, you can apply the same technique as well. And that's also something that I think is a very nice complement to logistic regression analysis. And so whenever I do a logistic regression, I'm pretty much always going to do an AUC just to get a sense of sort of the predictive effectiveness of the model as a whole and kind of have that sort of, R-squared-like thing to have in a logistic regression context. But before I do sort of end today, I do want to add kind of one note of sort of caution or thing to think about going forward. And that's that, really this question of what constitutes a good AUC value is something that's still kind of an open empirical question, right? It's something that varies by field, and that while there is this, this norm of 0.7 out there floating around, I've seen different numbers in different publications, and it's something I think is still sort of yet to be determined. And so, I would caution anyone from sort of taking this technique and looking at your model and saying, okay, we got 0.7, we're good. Maybe 0.7 isn't really good enough because, you could still have 0.8 or 0.9, and really the question of what constitutes an effective prediction really depends on what you think your goal is for predictive accuracy. And so this is just a measure. It shouldn't be treated in the same way as maybe some other statistical tests where you're just trying to get above a certain threshold to, say that something's significant or say that something matters. Here we really are getting a concrete measure of how many cases you're predicting. And so, having 30% of cases or 40% of cases that aren't predicted might not be something that, we can be satisfied with. We want to maybe push that AUC higher. Or conversely, if you're working with something that's really hard to predict, maybe something that's just better than 0.5 is good enough. So, I'd say a word of caution, sort of being open about how you're going to interpret that AUC is in order. Okay, well, that's all I have for today. So I'm ready for questions if anybody has those.
Great, thank you, Doug. So let me just scan down to see if anyone. Okay, so there is a question for From Rachel, is there a minimum N that is required to run ROC?
I'm not aware of a minimum N. In general, I think with most statistical tests, I get a little uncomfortable if the N goes down below 100. So I don't know, if you had 50 or 30. It really kind of depends on how confident you are running a logistic regression, because that's ultimately what's going to provide sort of the input for it. But I would sort of treat it like any other statistical analysis that you would do.
Okay. We have another question. I'm often asked how much better 0.7 is than 0.5. Is it fair to say that 0.7 is 40% better than guessing? And in parentheses, it says 0.2/0.5.
Yeah, I mean, I don't know if you would say 40% better than guessing, because, I think what makes the AUC useful is that it is pretty directly interpretable. So, the technically correct interpretation would be that you can predict, your odds of successfully predicting the outcome for a randomly selected case are 20% more, because, 70% is compared to 50%. So you've increased the odds that you will correctly predict cases. I think it's okay to say that you're predicting an additional 20% of the cases in your data set. So, that's kind of the frame of reference I would use. But I can see what you're saying, that it's sort of, increasing the amount that's predicted by about half, but it gets a little bit confusing because you're talking then about a proportion of what's already a percentage. So I would be inclined to just use the base percentage. But, I think probably the safest would just be to say it's an effective predictor at that point, and significantly better than chance.
Okay, Sonia says she's the one who asked the question. She says thanks. And then one person, this is kind of not related, but asked about the slides and recording. So I was hoping to get everybody, send people out a copy of the PowerPoint this morning. So if that didn't go out, then we will have everything available tomorrow on our website, on JRSA's website. If you go to our page on webinars, you will find it there sometime tomorrow. So we have another question. I'm not clear about how RUC is different from R squared. Aren't they both talking about how good the model is?
Oh, well, there is a difference, because the R squared, if you think about a linear regression context, it's really about the proportion of variation in Y that you're accounting for with a sort of regression line. So, it's looking at the distance between each of your data points and the regression line. The ROC curve is not so much about variation in values for the dependent variable as it is sort of the ratio of true positives to false positives. And so I guess maybe the simplest way to think about it for me is just to say that with the R squared, it's about how close your sort of predicted value is. So what you predict Y to be with your linear regression model to the true value of Y. So the true value of Y might be 25, and you predict 23, and so you're off by 2. But you're dealing with a dichotomous nonlinear situation when you're working with logistic regression. So, what you're really saying with the ROC line is that you're correctly predicting, if you've got an AUC of 0.7, you're correctly predicting 70% of cases. So you're correctly getting 70% of the time. So you're right on the money a certain amount of time, or you're completely off. You're either right or wrong with a dichotomous dependent variable. So you could potentially have a situation with R squared where your R squared could go up just because your predicted values get closer to your actual values, but you maybe don't actually predict more cases correctly. But with the AUC, it's about the number of cases rather than the value for the dependent variable. I don't know if that's clear or makes sense, but.
Okay. Okay. Oh, wait. Okay. So yes. So she's that person says thank you. Then we have another question. The field of predictive analytics seems to be exploding with a dizzying array of techniques and performance measures. Logistic regression and the AUC feel understandable and comfortable, but is this approach still considered acceptable in the criminal justice field, and for how long?
I would think it is. I think it's here to stay, I would think, because it is an effective measure and it is one that has kind of these advantages. It's not a new technique, but I think it is relatively new in criminal justice. I mean, as far as, within the past decade or two. So, I would think that it's here to be around. I'm not personally aware of something that's superseding it as of yet. So.
Well, I can say when I was in graduate school, I was just talking about this with a colleague. They did not teach AUC analysis, but just within the last year, I feel like I'm seeing it in so many different places within criminal justice research. So I really feel like it's being utilized so much more now, because just 10 years ago, I had never even heard of it. So I think like this is definitely researchers are utilizing this technique, and so I feel like we're going to keep seeing this and seeing it more in the future. Okay, so we have more questions. Steve, many of us work with 3 or 4 level classification instruments. Of what use is AUC with such instruments?
So let's see. So that's with multiple outcomes, I guess, is that question there.
That's what I think.
Yeah.
Yeah, that's what I think. I mean, and yeah. It's limited, right? Because it can really only be utilized to interpret the predictive probabilities from a logistic regression. So.
Right. So you would have to maybe get creative and sort of break it down into steps, or sort of figure out a way to kind of dichotomize it. If you had something where you could have sort of a process where somebody's being classified as one thing and then another thing and then another thing, if contingent on what they were classified already, you could look at each step individually, or figure out some way to kind of collapse them into groups that are dichotomous. But yeah, this isn't going to be a technique that you can use with multiple different outcomes.
Oh, I'm sorry. Okay, Steve, he wrote I misinterpreted. Not multiple outcomes. He's saying low, moderate, high, and very high.
Okay, yeah. So, yeah, well, I think one thing to think about, too, is that if you're thinking about the sort of risk assessment tool, that's the predictor, that's the classifier. So it's really the dependent variable that has to be dichotomous. So as long as you've got a dichotomous recidivism measure, recidivated yes or no, or something like that, then you could still use AUC analysis. It's just that the logistic regression model, when you save your predictive probabilities, is going to give you basically an interval probability that might not be perfectly tied to the thresholds. You could do an AUC analysis just on, the tool itself or the thresholds. You could have a variable that's 1 through 5 from very low to very high or something. And you could do an AUC analysis on that. It would give you a curve that would basically just have 5 steps. So it would be kind of a crude looking ROC curve, because it would just be your first discrimination threshold is, a score of 1 or very low. Your second discrimination threshold is a score of 2 or low. And your third discrimination threshold is a score of 3 and so forth. So you could still do it. It's just not going to be as sort of curvy as what you would get with predictive probabilities.
Okay. Kelly has a question. What are your thoughts on using the AUC statistics for validating pretrial risk assessments, particularly given that you don't have a true false positive rate for those that are high risk and detained, but would not have reoffended if released? I can repeat that if.
Yeah, maybe one repetition would be good, I
think. Okay, so what are your thoughts on using the AUC statistics for validating pretrial risk assessments, particularly given that you don't have a true, quote-unquote, false positive rate for those who are high risk and detained, but would not have reoffended if released?
Okay, so I guess what saying there is you've got people you've identified as high risk, but then you've removed them from the possibility of actually becoming a true positive because they've been given pretrial detention.
Yep.
Yeah, that's a tricky one because, obviously they can't become an actual false positive in that sense. I would think that the only way you could evaluate that would be to look at everybody who didn't get that. So what you've got is essentially kind of a skewed sample because your individuals that are identified as the highest risk are removed from the sample. But that would be sort of the same case if you were doing a recidivism study and you know, the highest risk people weren't released, they're just not going to be able to be observed. So, you know, that's just going to be a limitation to that study. But as far as a method, I think AUC would still be valid for assessing your false positive rate, or your ratio of your true positive, false positive rate for that population that's still out there and at risk of recidivating. It's just that the limitation would be that you know you don't have the true population because you've got this measure in place, detaining.
Right. Okay. No more messages coming in right now. Quick question. I was wondering, that article that you referenced, that 2009 article from Brennan, Dietrich, and I think it's Ered. I was wondering what journal that was from. People might be interested in seeing if they can find it. Do you remember the journal article?
Yeah, I've actually got
I'm sorry, the journal.
So, yeah, here.
Oh, okay, great.
Behavior, yeah. So.
Okay, great, thank you. So while I hope I still have some people, I'm going to jump a little bit and go and open the polling so that people can do that before they leave. Let's see. Give me 1 second. Is that working? Let's see. Okay. Oops, hold on 1 second, guys. There's usually like a run poll thing that we can't seem to find. Huh. Oh, I know why. I don't have the magic ball, guys. Okay, hold on 1 second. See, when you come to a JRSA webinar, we always like to have some fun here. So if you, Doug, if you can drag the magic ball to my name, that would be great. I am now, all right, here we go, opening poll. All right, guys, there you go. So everybody who's still on, if I haven't lost anybody, please take a moment to complete our poll. You're guaranteed for entertainment when Aaron Farley leads a webinar, that's for sure. Yeah. Okay, so let me just go back and check and see if we have any more questions before we finish. Okay. So it looks like we don't have any more questions. So Doug, I want to thank you so much for this presentation. I think it was really interesting, and we will have this posted again on our website hopefully tomorrow. And if there are any questions, you can follow up with us or Doug. I think we probably have your email address on our website as associated with the West Virginia SAC, so I know that people can find you through that. And I think that's it. Look forward to our registration opening for next month's webinar on ArcGIS. And thank you so much for attending, guys. Have a good afternoon. All right, bye.